Okay, I hope I'm audible to all my students who are attending this particular practice lecture for the statistical methods for economics course. Um, in this particular practice lecture, I'm going to solve a couple of numerical problems based on confidence intervals. In the last practice lecture as well, based on estimation and hypothesis testing, we had solved some good problems on constructing confidence intervals, be it for the population mean or for the population proportion. Okay, so in this particular lecture as well, let's solve one or two problems on how to construct confidence intervals or how to take into account the sampling errors while constructing confidence intervals. So let's quickly start with this particular practice lecture. So I am just writing the main heading for completeness. We are looking at practice problems on estimation and hypothesis testing. Practice problems on estimation and hypothesis testing. Okay, so let's quickly look at some practice problems. Let's look at question number 1. The mean and variance of a random sample, the mean and variance of a random sample of 64 observations were computed as 160 and 100 respectively. The first part of this question asks us compute the 95% confidence limits for the population. Compute the 95% confidence limits for the population mean. Let's quickly solve for the first part. I'm quickly writing what we are given. We are given that there are 64 observations, so n is 64. We are given that the sample mean is 160. The sample variance is 100. So the sample standard deviation will be square root of 100, which is 10. We all know from the lectures on confidence interval estimation, that the 95% confidence interval for the population mean mu, is given by, remember the formula, it's x bar plus minus z star alpha by 2 times the standard error of x. Okay, now x bar is 160. Standard error of x bar is sigma by root n. Sigma is 10. Root n is root 64. Root 64 is 8. Okay, so I have 10 by 8 and z star alpha by 2. Alpha is 5% because it's a 95% confidence interval. So alpha is 5%. 5% is 0.05 over 2, which is z star 0.025. If you check out the value from the z table, we all know it's 1.96 from the z tables. So my confidence intervals are x bar. If I just plug in the values here, it's x bar, which is 160 plus minus 1.96 times 10 by 8. How much is 10 by 8? 10 by 8 is 5 by 4. If I calculate that, comes out as 1.2. 10 by 8 comes out as 1.25. So the lower limit of the confidence interval is 160. So I can also write it as, first of all, 160 plus minus 1.96 multiplied by 1.25, which is 2.5. So my lower limit is 160 minus 2.45. It's 2.45. The upper limit is 160 plus 2.45. So 160 minus 2.45 is 157.55. And 160 plus 2.45 is 162.4. Okay, so this is our 95% confidence interval for the population mean mu. Let's look at what the second part of this question is asking us. So if I erase the first part off completely, erasing this part off, let us see what the second part of this question asks us. So erasing all this off. So part 2. If the investigator wants to be 95% confident that the error in the estimate of population mean should not exceed plus minus 1.4. How many additional observations are required? How many additional observations are required? This is an important part of this particular problem. Again, I am just writing what is given to us. We are given that the sample mean is 160 and the variance is 100. So the standard deviation is 10, which is square root of 100. Okay. If the investigator wants to be 95% confident that the error, what is the error? The error is nothing but the difference between the sample mean and the population. So probability of the error less than 1.4, less than or equal to 1.4 should be, our confidence level is 95%, so the probability should be 0.9. So if you read the first sentence, you will see that the probability of the sampling error less than or equal to 1.4 should be equal to 0.95. This is exactly what it means by saying that the investigator wants to be 95% confident, 95% confident that the error, which is this is my error, in estimation of population mean should not exceed plus minus 1.4. That means in absolute terms, modulus of x bar minus mu should be less than or equal to 1.4. So if I standardize on both sides, we know how to standardize. So what I do is I divide both sides by sigma by root. So mod of x bar minus mu over sigma by root n less than equal to 1.4 over sigma by root n is equal to 0.95, which implies probability of this is nothing but z less than or equal to 1.4. Root n goes on the top, sigma is here, equals 0.95. Okay. I need to find the n, because how many additional observations are required? We need to find the new value of n. So I can write this as phi of, so probability of z less than or equal to this, I can write it as phi of 1.4 root n by sigma is equal to 0.95. This implies 1.4 root n by sigma is equal to phi inverse 0.95. Okay, but hang on, it's a two-tailed test. Two-tailed test means if I use a two-tailed test, the 5% needs to be divided further into two parts. This is 0.025. This is also 0.025 because they should sum up to 0.05. That means this whole area ideally will be it will be 0.975. So I think the kind of tables we are using, let's use 0.975. So since it's a two-tailed test, it's 0.97. Here also it's 0.97. So what is my root n? Why have I taken 0.975? I'm repeating it again. It's a two-tailed. So 5% gets divided into two parts, 2.5% and 2.5%. So my Z tables give me everything to the left of that. So this value is such that everything to the left of it is 0.975. Because this particular part is 0.95, to that I add 0.025, so I get 0.975. So my root n will be 0.975 into sigma over 1.4. Now what is sigma? Sigma is 10 over 1.4. So if I solve this further, for which I erase this particular part off, I can write that root n is equal to, now we can use our calculator. So it's going to be 0.975 multiplied by 10 divided over 1.4. Comes out as 6.96 approximately. So my n will be 6.96 square, which comes out as 48.4. 48.4. Okay, so this is what I get once I solve for n. Okay, let me see if I have not made any error. Let me just verify the question once. Okay, I think I made an error here, students. If I solve it from here once again, just to rectify the error I have made. So this step is correct, this step is correct, this step is correct. And here I've taken, instead of 0.95, why have I taken 0.975? Because it's a two-tailed test. So 1.4 square root of n over sigma, I can write as phi inverse of 0.97. I can write this as phi inverse of 0.975. So now from the Z table, I need to find how much is phi inverse of 0.975. So if I come to the Z table, so let's scroll down the Z table and let's figure out how much is going to be 0.975. So if I scroll down the table, let's scroll down the table and let us see what it comes out as. So 0.975 comes out as here. 0.975 is coming out here. So it's 1.9 under 0, 1, 2, 3, 4, 5, 6. So my answer is 1.96. So I can write 1.4 square root of n over sigma is equal to 1.96. So root n is 1.96 into sigma divided by 1.4. So I can write therefore root n is 1.96 into how much is sigma? Sigma is 10 because variance was 100. So sigma is 10 over 1.4. So if I calculate this, it's 1.96 multiplied by 10 divided over 1.4 comes out as 14. So square root of n is 14, which implies my n is 14 square, which is 196. This is my new sample size. What was my initial sample size? 64. The new sample size required for the investigator to be 95% confidence about the sampling error is 196. So how many additional observations are required? If I erase this particular part of I can write that additional observations required. I can write that the number of additional observations required, the number of additional observations required is equal to 196 minus 64, which is 132. This is the answer for part 2 to this question. There are 132 additional observations required for the investigator to be 95% confident that the sampling error will not exceed plus minus 1 point. Okay, let's look at one more practice question in this particular lecture, question number 2. A research worker wishes to estimate the mean of a population, by using sufficiently large sample. By using a sufficiently large sample, the probability is 0.95 that the sample mean will not differ from the true mean, from the true population mean by more than 25% of the standard deviation. By more than 25% of the standard deviation. The question asks us how large a sample should be taken. Indirectly, the question is asking us what should be the sample size. Okay, so a research worker wishes to estimate the mean of a population. So I can write, let mu denote the mean of the population. Let mu denote the mean of the population. And let x bar denote the mean of the sample. So what do we need to find out? The probability is 0.95 that the sample mean will not differ from the population mean by more than 25% of the standard deviation. So the probability that the difference between the sample and the population mean in absolute terms should be less than or equal to 25% of the standard deviation, and the probability of this happening should exactly be equal to 0.9. The probability of mod of x bar minus mu less than equal to 25% of sigma should be equal to 0.95. So if I solve this, this is mod of x bar minus mu less than equal to 25% of sigma, means 25 by 100 multiplied by sigma equal to 0.95. This I can write as mod of x bar minus mu less than equal to sigma by 4 equals 0.95. To convert to z, I divide both sides by sigma by root n. So mod of x bar minus mu over sigma by root n less than or equal to sigma by 4 divided by sigma by root n is equal to 0.9. This whole term I can call it as z. So probability of mod of z less than equal to sigma by 4 divided over sigma by root n, I can also write as root n by sigma, equals 0.95. This and this cancel out. So probability of mod of z less than equal to root n by 4 is equal to 0.95. Not mod of z actually. This is, I can take it as, first of all, so if I take mod of z, remember again it's a two-tailed test. It's a two-tailed test. Instead of 0.95, I'll have 0.97. So, you know, it's like saying that till here there were no mods. So when I take 0.95 here, then it means that I'm not using a two-tailed test. Since I'm using a two-tailed test, I'll use 0.975. Again, this I can write as phi of square root of n by 4 is equal to 0.975. So square root of n by 4 is phi inverse of 0.975. Okay. How much is phi inverse of 0.975? In the last question only we found out that phi inverse of 0.975 is 1.96. So I can write root n by 4 is equal to 1.96. So root n is 1.96 multiplied by 4. What does it come out? It comes out as 7.8. So my n will be 7.84 squared up, which is going to be 61.46. It's going to come out as 61.46. So I can write that approximately 62 observations. So n should approximately be 62. This is the answer for this. The catch here is that students should not get confused. I took 0.95 here, but the moment I use the two-tailed test, I should have not used 0.95. I should have, like from the beginning only, I should have used 0.975. So in case students are getting confused, use 0.975 from the very beginning. Because I have a mod here. Mod means it's a two-tailed. Two-tailed means it's 0.975. Even in the previous question, you can start with using 0.975 from the very beginning. Because when I draw a diagram, 5% is divided into two parts. This is 2.5% and this is also 2.5%. Now 2.5% is, so this particular part will be how much? So this particular portion is 95%. 95% plus 2.5% is 97.5%, which I can write as 0.97. That is why I am using 0.975. So instead of writing 0.95, I think it's better to write 0.975. Because the kind of Z tables I use, which are the Devore Z tables, will give you the Z value, will give you that Z value such that you have all the area to the left of it. And all the area to the left of this particular Z value is 95 plus 2.5, it's 97.5. So hoping all students have understood how we have solved for this particular practice question. I stop in this lecture. In the next lecture, in the next practice lecture, we are going to look at numerical problems on hypothesis testing. Numericals on hypothesis testing. We are going to do some practice problems on hypothesis testing in the next lecture. I stop in this particular practice lecture. I hope students have enjoyed this lecture. Any doubts? You can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolofeconomics@gmail.com. This is where I stop in this lecture.